So excuse me, in Unit 6C, we're going to talk about normal distribution. This will be the last topic we discuss before our exam. Normal distribution is a huge part of a statistics course. We're just going to briefly touch base on it and kind of see, some of the advantages to working with normal distribution. But again, if you want to really get in depth to normal distribution, you're going to have to take an intro statistics class. But we'll just kind of cover some of the basics of normal distribution. Okay, so one of the first things is let's talk about what normal distribution is. The normal distribution is a symmetric bell-shaped distribution with a single peak. Its peak corresponds to the mean, median, and mode of the distribution. Its variation is characterized by the standard deviation of the distribution. In general, let me see if it's on the next page. In general, this is like kind of our general graph of the normal curve, okay? And then when it's in standard normal, so this is standard normal distribution, we're gonna have a mean of 0, so this is our mean. And then we have standard deviations of 1, so they kind of go out like this, and it's supposed to be symmetric, by the way, I just can't draw, and then like this, and like this. And this is -1, -2, -3, and this is 1, 2, and 3. And these are standard deviations. This is how far our relationship is to the mean. So in general, standard deviation kind of talks about the idea of relative standing to the mean. So it's something that we're gonna talk about in this section quite a bit, okay? Now, the normal shape, this figure below shows two distributions, a famous data set of chest sizes of Scottish militiamen collected in about 1846, and the distribution of population densities of the 50 states. Is either distribution normal distribution? Explained. So if you look right here, if I were to try to draw this, it kind of looks normal, right? Or approximately normal. We might say approximately normal. And this definitely is not, right? This would be right skewed. Okay, so this is from the previous chapter, we would talk about right skewed, right? So this one is approximately normal. It's not obviously perfectly symmetric. So a lot of times we talk about normal distribution and approximately normal distribution. Most of the time we treat them kind of the same. It's almost symmetric and has this nice little smooth bell shape. So again, that's what we're looking for normal distribution. And then this is definitely not normal distribution. This is more like right skewed, okay? So the distribution of chest sizes is nearly symmetric with a mean between 39 and 40 inches. Values far from the mean are less common, giving it the bell-shaped curve. So again, this is what we're looking for from our normal distribution, is a bell-shaped curve. The distribution in figure 615 shows most states have low population densities, but a few have a much higher population density, like California and New York. This fact makes the distribution right skewed, so that's what we were talking about. So it is not normal, okay? So conditions for normal distribution. So a data set satisfying the following criteria is likely to have nearly normal distribution. Sometimes they call this approximately normal distribution, okay? So most data values are clustered near the mean, giving the distribution a well-defined single peak. So like this, right? We're really looking for this one peak. Data values are spread evenly around the mean, making the distribution symmetric. So once again, we're really looking at this graph. This one obviously is not normal distribution. And then this is kind of my drawing right here, right? This is kind of that one peak. Everything's kind of spread out, clustered in the middle, and then it spreads out throughout the graph as you go further and further away from the mean. Okay, so spread evenly around the mean, making the distribution symmetric. That's what we're looking for. Larger deviations from the mean are increasingly rare, producing the tapering tails on the distribution. So once again, what they're talking about is here's one standard deviation, two standard deviations, three. So look how far we are over here. There's hardly any area under the curve right there. Again, if you compare it to look right here. So here's one standard deviation left and one standard deviation right. Look how much is in here. Look how much area is in here, okay? So there is a big chunk of the area in that one standard deviation. And then if we go two standard deviations out, look how much of the area is under this curve. So in a pure statistics class, we would be talking about this area under the curve as probability. Now we're going to use normal distribution to help us figure this out. But for our class, everything kind of has to be nice in terms of distribution. We are going to kind of rely on a little bit of z-score tables, but we're not going to go too in depth into that. Okay. And lastly, individual data values result from a combination of many different factors. Okay, well, that's that's kind of a catch-all. That could be anything. Okay, so it says, which of the following variables would you expect to have a normal or nearly normal distribution, or approximately normal? Scores on a very easy test, or foot length of a random sample of adult women. So scores on a very easy test. Wouldn't you think that it's going to be, you know, something, I don't know the exact look of it, but if we were going to do it in scores, let's say that this was, you know, 100%, this was 50%, and this was 0%. Or yeah, let's do 0.5 and no, you know what? I want to do it a different way. So basically what I want to think about, let's explain it. So on part A, scores on a very easy test. Would you guys not assume that if the test is very easy, a huge chunk of the class is going to score very high and a small portion will score very low? So you could have something like this, right? So you could have a curve that goes like this, like that, or something like that. But again, it's not going to be, how do you say this? It's not going to be symmetric with just as many people doing poorly as people that did well, because if it's a very easy exam, that means the majority of people are going to score very high, and there won't be a lot away from that center value of the high scores. And so again, we're thinking of the mean will be high with many scores near the max. Okay, with very few lower scores. Okay. So we would expect this to be, well, actually it might go like this, realistically, very low and then up to here. So then it would be something like that. So we would expect it to be left skewed, I believe. Okay. Now, what if I do another one for foot lengths? Well, foot lengths, and again, this is randomly chosen. And it's a foot length chosen by a lot of different factors, you know, gender, genetics, all these different things. That's kind of what I think they meant by this. Individual data results from a combination of many different factors. So it could be from genetics, so on and so on and so on. Environmental factors. So we therefore expect the lengths of women's feet to cluster near the mean and become less common further from, was it for women only? Random sample of adult women. Oh, sorry. So I thought it was for men and women. It was just for adult women. So we would probably expect it to be something like this. We expect there to be a lot near this center right here, right? We expect there to be a lot kind of bunched up here near the center. And then, you know, we always will still have the extreme, you know, large sizes or small sizes, you know, and stuff like that. But in general, we would expect it to be somewhat symmetric, okay? Let me see here. So this is called the empirical rule. Okay, so does your book give it a name? No, your book does not give it a name. So this is called the empirical rule. So the empirical rule basically tells us that if you go, if you go one standard deviation, that's not going to show up. So if you go one standard deviation like this to the left or the right of the mean, so this symbol right here of sigma, so that symbol means sigma, that equals standard deviation. And again, the standard deviation is basically saying how far away from the mean you are. And we count it in numbers of standard deviations. So in general, we need to know the standard deviation for the data, and then we can count how far away we are, how many of these standard deviations. That'll be something we call a z-score. Okay, so what they're saying is that if you were to shade in this area right here, and you were to count just this area and how many scores, they're saying that approximately 68% of all the scores would be found in between one standard deviation, left or right. So imagine you had 100 scores. That means that approximately 68 of those scores would be somewhere in this range. Okay. Now, what they say next is if you go 2 standard deviations, so now you're way over here, and then you were to shade in this area. They're saying if you had 100 scores, let's say test scores, 95% of them, 95%, right? So they go from here to here, 95% are in this little shaded area. Meaning if you had 100 scores, 95% of the people, or 95 scores, were between -2 and +2 standard deviations, okay? And then they say, if you go way out here, there's hardly any area left. Notice there's hardly anything over here on the sides. They're saying in between here, 99.7%, or 99 out of 100 scores, almost 100 of the 100 scores will be between -3 and 3 standard deviations, okay? Or within 3 standard deviations, plus or minus, okay? So for the empirical rule, we have within 1 standard deviation, 68%, okay? Then within 2 standard deviations, 95% of all values or data values, and then within 3 standard deviations, 99.7% of all data. So if you know that if somebody asks you, is it possible that you score more than 3 standard deviations above the mean on your test? The likelihood of you doing that is 0.15%, half of the little bit of area that's left over on the side. So there's very little values over on this side. There's almost nothing over there, okay? Almost 0%, okay? So let's look at this. It says about 68%, it's 68.3, but for our class, we're gonna use 68, or just over 2/3 of the data point values fall within 1 standard deviation. About 95%, and again, we're not gonna use these percentages really, we're gonna focus on the nice clean ones, of the data points fall within 2 standard deviations of the mean, and about 99.7 of the data points fall within 3 standard deviations of the mean. Applies to values that are exactly 1, 2, or 3. So remember, for us, it would have to be exactly to use the empirical rule. Okay, so that's what the empirical rule says. Now, what if you're 2.7 standard deviations away? Well, then the empirical rule doesn't help us as much. We need something else. Okay, so it says in this first example, vending machines can be adjusted to reject coins above and below certain weights. The weights of legal US quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.07 grams. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected? So what I would do for this problem is I would draw my little standard deviation, my graph of normal distribution, okay? And then right here in the middle is the mean. So normally it's 0, okay? So this is always the mean right here. Okay, it's the smack dab in the middle. Okay, now the thing is for this problem, the mean is actually it says normally distributed with a mean of 5.67. So I'm going to do 5.67 right here. Okay, and then it says it has a standard deviation of 0.07. Okay, so I'm going to add 0.07 and subtract 0.07. Okay, so I'm going to take out my calculator. And I'm going to do 5.67 plus 0.07, and I get 5.74. And then I'm going to do 5.67 minus 0.07, and I get 5.6, okay? Now I'm gonna do another standard deviation. So this will be my second standard deviation that way, and this will be my second standard deviation that way. I'm gonna add 0.07 again, so this should be 5.81, and this should be, what? 5.53. Let's do 5.6 minus 0.07. That should be it, yep. Now, notice this is two standard deviations, right? So here's one standard deviation. This is -1, and this is -2, and this is 1, and this is 2, okay? So I got 5.81 when I went 2 to the right in standard deviation, and I got 5.53 when I went 2 to the left. They want to know if a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what part of the graph are they asking? Are they asking for this middle part, or are they asking for the part not in the middle? So now think about this. They're saying these two numbers are special because these are two standard deviations away. So two standard deviations, right? Well, how much data is in the middle? Okay, well, let's go back up to the empirical rule. It says will fall within two standard deviations, 95%. So that means that this middle part right here is 95%. So this section right here is 95%, but they don't want that percent. They want this over here and this over here, okay? So it says what percentage of legal quarters will be rejected by this machine? Now think about it. You got this area and this area. How are we going to find that? Well, if 95% is in the middle, how much are on the edges? Well, that means that this has to be 2.5% and this has to be 2.5% for a total of 5%. So we have, or the machine will reject approximately 5%. Okay, so it will reject approximately 5% of the quarters. Okay. Okay, so let me turn the page real quick. So now let's look at this next one. Okay, so it says standard scores. Now we're going to talk about z-scores, okay, or the standard score. So a z-score is extremely important in statistics. Z-scores help us talk about relative standing in relation to the mean, which is basically standard deviation. So a z-score is basically standard deviation, but put in a very specific format. And whenever you say your z-score, it's supposed to mean something to you. Like if you scored on my exam a 3.1 z-score on my exam, that's amazing. Because think about it. If I gave you an exam and I said the mean was a 73 and it had a standard deviation of doesn't matter. Oops. Let me draw my picture. Sometimes I do better when I draw a picture. Okay, so let me draw my mean. So let's say my mean was 73 and you go over 1, 2, 3 standard deviations. Oops. We got to do 0, 1, 2 because this is the standard normal. What I was drawing was the non-standard normal or unstandardized normal distribution. So we're going to go there, and then over here we're going to go -1, -2, -3. And again, it's supposed to be symmetric. I just can't draw. So if you scored a z-score of 3.1, okay, is that good? Okay, so the thing is, think about it. You scored a 3.1. That means you're here somewhere, right? 3.1 is here. That means that you're in this percentile. How many people actually scored higher than you? Now, if we go back and look, it says 99.7 is within 3 standard deviations. You're over here somewhere. You're above that. So that means there's probably no one that scored above you on the exam. So I don't even need to know what the mean is. I don't even need to know what the standard deviation is. If somebody tells me this was your z-score on the test, I know I did amazing. Now, what if they told you you did a -2.1? That means you're to the left of the average, the left of the mean, meaning that you're below the rest of the class by 2 standard deviations. So you're in the bottom 5% or 2.5%. Okay, so not a good place to be. So that's why you want to understand what z-scores are, because just by mentioning your z-score, you know something about it, where you're located at in this graph right here. Okay, but that's the standard normal. Okay, so here's how we can find a z-score. So it says we take the data value minus the mean and then divide it by the standard deviation. Okay, so to find a z-score, we need to know the mean and the standard deviation. All right. Now there's other ways we can work around it. I've also seen it written like this in my statistics class. We say x minus x bar divided by sigma, which is standard deviation. That's the same one they used up here, you guys, right here. This is sigma, right? So if you're above the mean, you have a positive z-score. And if you're below the mean, you have a negative z-score. Okay. And I have a few examples that we're going to do on a separate thing after this, but let's just do a few of these from your book. So it says the Stanford Binet IQ test is scaled so that scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the standard IQ scores for an 85, a 100, and a 125. So let's do for the 85. Okay. So we want to find a z-score for 85. So that means we get z equals, and then according to my formula, we're going to take the data value minus the mean. Okay, so data value, which is 85, minus the mean. They told us the mean was a 100. And then we're going to divide it by the standard deviation, which they said was 15. So I get negative 15 over 15, which is equal to negative 1. So you have a z-score of negative 1. So that's actually not a good IQ score, right? Because you're negative 1, meaning you're 1 standard deviation below the mean. That means you're below the average score. Okay, so not great. All right. Now we do z equals, and there's a lot of contributing factors to this. So that's my score of 100 minus the mean divided by 15. So I get 0 over 15, which is equal to 0. So that means I have a z-score of 0, which means you're right at average. You're right at the mean. So a 100 on the IQ score, according to this, means you're right at the average. Okay. So there's that. Now let's do it again. So z equals, for now, let's do for 125. So I'm going to do 125 minus the mean divided by 15 equals 25 divided by 15. Let's divide these by 5. This would be 5. This would be 3. So we get 5/3, which is what, 1.6? Oops, no, 1.67. Let's round off. Okay, so approximately 1.67, right? Because it's actually 1.66666666. So 5 divided by 3. Yep. All right. So this is our z-score of 1.67. Now this is actually, because it's positive, that means you're above the average on the IQ scores. So you're in the upper percentiles, right? Okay, so this is how you can find z-scores based on information given. Okay. Now, it says the percentile of data value is the percentage of all data values in the data set that are less than or equal to it, okay? A data value that lies between 2 percentiles is said to lie in the lower percentile, all right? So that's just some clarification. Here's the tables we're gonna use to find percentiles of z-scores. Now, again, it kind of goes, it's a little bit different than the z-score I normally use. So it'll take me a minute to also use this table, but it goes like this. Negatives it goes from bigger to smaller, keeps getting there, and then it just keeps going like this. Okay, so on and so on. And then this one starts at -2. So I think what they're supposed to be doing, I think they couldn't fit it on one page in the notes. So I think it's supposed to go all the way down to here, you guys. And it just keeps going, and then it wraps back up here. Okay, now these are called the percentiles, but they're actually 0.1587 or 0.1711. They're actually decimals, but you could think of it as a percentage as well. Okay, so here's how we can use it. So let's take a look at this. It says cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. So just so you guys know, this is information about this curve right here. Okay, so if I had this curve, okay, what they're saying is that if you were right here at -3.5 z-score, how much data is to the left? How much is over here? And they say 0.02. Okay, so that's actually of a percentile. So that actually means 0.02 percent. So that's, if you think of it as a decimal, that's 0.0002. That is a very, very, very small number, okay? So I could check it on my calculator. You guys don't have a calculator, but we could say negative 3.5. Yep, okay. So you guys don't have the graphing calculator. If you do, you could show up to class and ask me how to use the calculator to calculate these values. I don't think there's enough people that have a calculator, so I'm not gonna present it here. But if you do wanna try to use your graphing calculator, TI-84 Plus, TI-83 Plus, TI-84 Silver Edition, something like that, I can show you how to do that if you want, okay? So what we're gonna do is, cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178. So we know the mean equals 178 and a standard deviation. So standard deviation equals 41. And you could call this sigma, right? And this is X bar. Those are the notations that I normally use. Or they just call it mu as well, since this is for a population, okay? So it says, in what percentile is 20-year-old man with a cholesterol level of 190? So what I'm going to do is 20-year-old with cholesterol levels of 190. Okay, so let's do this one first. So what I'm going to do is they want to know the z-score for this basically. So I have to create a z-score and then find the percentile of that z-score. Because this table doesn't have 190 cholesterol, this only has z-scores, we have to standardize this. We have to convert it. So we have to standardize 190, okay? So we have to make 190 into a z-score. Where does that fit? So if they, and we're assuming it's normally distributed, oops. So if we were to do this, oops, okay, what was the mean of this? It's 178. So the mean would be 178 and 190 would be over here somewhere, right? So they want to know, what is that percentile? How much is below it? How much area is below it? How many of the data values are below it? So the thing is we have to, how do I say this? We have to attempt to put this in terms of z, because then if we know the z-score, we can find a comparable value here on our table. And I'll show you how to use that right now. So it says we have to find z. So z is equal to 190 minus the mean of 178 and divided by the standard deviation of, what did they say, 41. So I'm just going to take out my calculator and I'm going to approximate this. So I'm going to say 190 minus 178, and then I'm going to hit enter and I'm going to divide by 41. Oops, did I do something wrong here? 190 standard data value minus the mean. Let me see here. So I have a z-score. So actually I drew that incorrectly. I fooled myself. If 41 is the standard deviation, that means that if you go from 178 plus 41, I deceived my own eyes. That means our first standard deviation would be here at 219. So where is 190? 190 is like probably right here, right? So that's 190. So they want to shade all this and they want to know how much area is right there, okay? So we get a z-score. I get a z-score of 0.29268, so on and so on. Now, if you look up here, all of their z-scores are only one, oh no, they have 2 digits, it looks like. Let me see here. It looks like they do 2 decimal places, so let's do 2 decimal places for ours as well. So we're going to say that this is 0.29, okay? So then what I'm going to do is I'm going to come and I'm going to find my z-score of 0.29, okay? So let's see here. I think it's up here. Okay, so, oh, they don't even give us a full z-score list. Okay, let me go through. I thought this was the same as my table, and I thought it would be easy to work with, but I got to go through this real quick. Okay, so you have to decide, is it closer to this one or to this one, right? Where was 0.29 going to be? 0.29 looks like it's closer to 0.3, okay? So what I have to do is I'm going to round off to 0.30, all right? And then I'm going to look at the percentile, which is right here, okay? So points are 61.79. So we get a percentile of, what was it? Let me double check, sorry guys, 61.79%. So it's really 0.6179. But if you wanted to round off, this would be 0.62, or in your book, they'll say that it's 62%. This, and this are all the same. Now, this isn't actually correct because remember, we actually got 0.29, and there's not really, and again, that was even rounding off, and there's not exactly a 0.29 here. Remember, we had to decide, is it closer to 0.25 or is it closer to 0.30? It was closer to 0.30, so I chose this percentile, right? If it was like 0.26, then I would have chose this and I would have got 60%, okay? So what this is telling us is if we come back here, that means that if we were gonna calculate, let's say I wanted to calculate this area, how much area is in there? There's approximately 0.62 of the whole thing, right? So the whole thing is 100%, right? Or 0.1 or 1. This is 0.62 or 62% of the area is below 178. Okay, so if we were to calculate, let's say there was 100 scores, that means that 62 of the scores are lower than 178. That's what that's telling you. And whenever you're doing this table, these percentiles are always what's below it on the left-hand side. Okay, there's ways that you can outsmart it, but in general, that's what it's saying for that. Okay, and I think that's it for this section. So I wanted to do a few extra problems. Once again, here's the empirical rule. And don't worry about this one, by the way, that's the, that gives you the much more exactness. We want to focus more on the big idea of the 68, 95, and 99.7. So this problem says IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15, just like before. Draw the distribution of the empirical rule. So what I could do is I could draw this. Oops, geez, that's terrible. Sorry about that, guys. Okay, and what would the center be? What would the mean be? Well, if the mean is 100, just like here, instead of putting 0, we're going to put a 100 here. Now we're going to go left 1 and we're going to go right 1 standard deviation, but the standard deviation is 15, so this will be 115 and this will be 85. Then we're going to go one more, this will be 130 and this will be 70. Then we're going to go one more, this will be 55 and this will be 145. Okay, so it's basically the same graph as this one, except instead of using 0, 1, 2, and 3, which is standard, so this is standard, we're using non-standard or unstandardized or non-standardized. But the idea is that this graph should match this graph in terms of percentages and area covered and everything like that. Okay, so now that we have that, it says, according to the empirical rule, what percentage of IQ scores are between 70 and 130? So let's see, let's shade. Here's 70, and we'll shade all the way up until 130. What percentage is in between there? Well, that's 2 standard deviations to the left or the right of the mean. That would be 95% or 0.95, oops, 0.95 area, okay? So area under the curve in this case is percentage of the data, okay? So according to the empirical rule, what percentage of IQ scores are above 145? So now we got to start over here and we got to say above 145. So how much is up here, right? Because it goes on forever, by the way. There's just so little over there that we don't count much of it. Well, I know that from here to here, that's 3 standard deviations, right? How much data is in there? Well, according to the empirical rule, 99.7% is in the middle, right? Is in between 3 standard deviations. Well, then what's left over? If I do 100% minus 99.7%, I end up with 0.3%, okay? But remember, this is symmetric. So that means that this 0.3% that's left has to go here on this side, but it also has to go over there. So then I take 0.3% and I divide it by 2 and I get 0.15% or 0.0015. Okay. So in terms of percentage, it's 15 hundredths of 1% is up here. So this area right here is 0.15. Crap. This area right there is 0.15%. So people that score above 145 are in the basically the 1500ths top percentage. Okay, they're the top, very small percentage of the population that could do that. According to the empirical rule, what percentage of IQ scores are above that? So I'm going to say 0.15%. So very, very little is above. Okay, I just wanted to give you guys a little bit more practice with this. Okay, now here's a problem. Don't worry about example 13. This is just call it an example. Okay, it says if we wish to compare data in different data sets or within the same data set, we need some measure of relative standing. Measure of relative standing tells us where a particular data value stands in relation to the other data values in the set, the z-score. Okay, so z-score is the number of standard deviations that an observation from value x is above or below the mean. This value standardizes the values so they can be compared. Okay, so that way we can talk about, you know, your score versus my score in terms of comparison to the mean, okay, or comparison to each other as well. So the distribution of heights of women aged 20 to 29 is approximately bell-shaped normal with a mean of 64 inches and a standard deviation of 2.7 inches. Men the same age have heights that follow approximately normal distribution with a mean of 69.3 inches and standard deviation of 2.8. What are the z-scores for women who are 6 feet tall and a man who is 6 feet tall? And remember, 6 feet is 72 inches. Okay, so what we're going to do is we're going to find women's z-score. Oops. So z equals, now a woman's z-score that is 6 feet tall would be 72 minus the mean. What is the mean for women? Women have 64 inches, so 64 divided by a standard deviation of 2.7. Okay, and now let's do for men. Men have 72 inch, so a 6 foot tall man minus what's the mean height for men? 69.3 right here, divided by the standard deviation, which is 2.8. Okay, so let's see what we get. And I'm going to round these to 2 decimal places. So this will be 8 divided by 2.7. So this will be 2.96. Yeah. And then for men, 72 minus 69.3 divided by 2.8. And I get 0.96. Yeah, let's say 0.96. So this is a z-score that's about 1. This is a z-score that's about 3. Okay. Now it says, is it unusual for a female to be 6 feet tall? So think about this. Okay. So here's the mean. For women, the mean is 64. And then if we go 1 standard deviation over, we'd be at 66.7. And then if we go another standard deviation, we'd be at what? 69.4. Let me see. 64 plus 2.7 times 2. 69.4. And then if we go over 3 standard deviations, we'd be at 72.1. Okay. So, and remember, the empirical rule says in a normal distribution, or not even the empirical rule, but in normal distribution, look from here to here, how much of the data is there? 99.7%. So once you get past 2 standard deviations, it starts getting a little bit like unusual for that to occur. Well, in this case, a woman that is 6 feet tall is 2.96 standard deviations. So that would be right about here somewhere, right? Almost at 72.1. So I would definitely say, yes, unusual. And the rule of thumb is normally 2 standard deviations, okay? Now for men, for women, Well, let's look at the drawing for men, okay? So right here's the mean. What's the mean for men? 69.3. And then we're going to walk 2.8. And that'll be right here. That'll be 72.1. Then we're going to walk another 2.8. And that'll be 74.9. And then we're going to walk another 2.8. And that'll be 77.7. Okay. Now, so this is 1 standard deviation, 2 standard deviations, 3. We're at 0.96. So we're like right here somewhere, right? That's where 72 is, right? So 72 is like right there somewhere. Okay. So we're not even 1 standard deviation. Is that unusual? Isn't it say that 95% of the data is in here? So that's not unusual at all. So we would say no, not unusual. That's a lot of negatives in one sentence, but you guys get the idea. I just wanted to show you a few of these problems, guys, so you can have a little bit more practice when you go to do your homework. But thanks for watching the video, and that'll do it for today.